Greetings. Let's talk a little bit about Newtonian gravitation. We're going to start off kind of talking about Kepler's laws, because I'm going to assume you can figure out the bit about gravitational force and get that out of the textbook. So this is kind of an interesting consequence and a good place to kind of jump in and start talking. So there are three laws that Kepler proposed about the motion of the planets, basically. So yeah. We got a whole bunch of data from Tycho Brahe, and then Kepler basically put the data together and figured out these laws. And then Newton basically says, hey, look, my gravity justifies these. You can get these laws that Kepler got from the data, I can get from my theory of gravitation. So first one, law of orbits, basically says that the planets move in an elliptical orbit with the sun as a focus. So this here is an ellipse, sun at a focus. For the most part, we're going to generally assume things are circles, but most of our results, without fail, hold with kind of this assumption, where the radius of a circle is replaced by the semi-major axis of an ellipse. So yeah, that's about that. Second law, law of areas. This is where it gets a little more interesting. We'll dig into this one physically in a second. It basically says that in equal times, the planets carve out equal areas, which is a little kind of convoluted sounding. But what you're saying is that basically the rate at which the planets carve out and sweep out an area is equal. So, in this case, it's going faster linearly in order to carve out an area. In this case, it's going slower. We can think about this kind of simply from an angular momentum conservation perspective, where if we have, I omega 1 equals I initial, omega initial equals I final, omega final. If the planet is closer, I is smaller, omega is bigger. If the planet is further, I is bigger, omega is smaller. It's kind of an easy way to think about it. And the last one, law of periods, which I don't have a picture for, basically says that the square of a period is proportional to the cube of the radius. But I can justify it numerically, so that's kind of exciting. Let's go with the law of areas, though, for justifications first. So law of areas, if we're looking at this, here is our kind of terrible ellipse. Let's try that again. Less terrible ellipse. Here is the sun as our focus. Here is our planet on this little path. So we're going to make a couple of simplifying assumptions here. We're going to say that this is some small angle, d theta. This angle is so small that basically, the distance along the middle here of this triangle is what we're going to call r, and it basically stays r, even though that's physically impossible. Because I'm also going to say that this bit here at the end is then r d theta. So if we take that to be the case, then the area of this little chunk is 1/2 r, which is our height, times r d theta, which is our base. So this is our little area. At the moment, we're basically thinking of this, for a circular orbit. This is simple to consider. So for a circular orbit, I can also say that 1/2 r squared d theta dt, since theta is the only thing that's changing, is then equal to dA dt. Well, 1/2 r squared d theta dt is 1/2 r squared omega, right? And so that is then 1/2 RV. Bear with me here. Which is 1/2 L over m. So we've said a couple times in class that there is no net torque in this situation, because gravity acts along the separation, so it acts along the distance to the axis. So L is constant. Angular momentum is conserved if there's no net torque. If L is constant, then this rate dA dt, at which we're sweeping out these areas, is constant. And this generalizes to the whatever elliptical case. Your book has the variation of that. So that's just kind of like, it's an interesting thing to think about. So you get this experimentally when you're talking about it. And here we're just saying, all right, since gravity is basically a central force, it's acting radially inwards. Because of that, there's no torque. Because of that, there's conservation of angular momentum. Because of conservation of angular momentum, we can explain this whole bit with the areas and their orbits. It's a very neat thing. It's kind of nice to kind of come and get some predictive elements of this for things that aren't just like, oh look, a ball, it dropped, my goodness. Moving on. Let us consider the puzzling case of this law of periods. And the law of periods, in case you forgot from about 4 minutes ago, made this claim that the period of the square of a planet's period is proportional to the cube of its radius, or the cube of its semi-major axis. Specifically, it says this, that there is this crazy, messy, horrifying thing. That's a G, not a 6. Which doesn't really make it terribly clear what you're looking at. So where does this come from? Well, let's pause there for a second. All right. If we think about this, if we're going in a circle, and again, this will apply basically for elliptical stuff too, if we make an allowance that R and A are equivalent, and not justifying it, but you could do it if you really felt inclined. We know that we have to have some centripetal force. And in this case, the only force acting is gravity. So let's say that mv squared over r is equal to g mm over r squared, where little m is the orbiting body, or let's just say planet. Planet makes more sense. Is the planet, big M is the sun. Or little m is the moon, big M is the planet, orbiting body, orbited body. That starts to go around in circles in my head and I get worried. So this V isn't yet related to a period. So let's think about this. So I could rephrase this instead as being m 2 pi r over t squared over r equals g mm over r squared. Right? Because my velocity is going to be the circumference divided by the period. Reasonable. And again, if we think about this, it's hard for us to measure the radius of a planet necessarily. It's kind of a tricky thing to get at, but the period is something we're interested in. Our planet, at least, it's hard to measure the radius. Other planets we can do a little bit better. It's mind-boggling to think of the data you would collect, but it can be done. All right, so anyway, if we do this, let's get rid of these m's. So we've got 4 pi squared r by t squared is equal to g big M by r squared. And we can kind of already see where this is going. Pull the t squared up top and kind of flip things around. We've got 4 pi squared divided by gm, and then we get an r cubed, which is, astonishingly enough, the claim that we had made. And so again, from this idea saying, again, all we're saying is that this thing is going in a circle, or an ellipse, but it's circular enough that we can take this to first approximation. We're saying, all right, it's going in a circle, there has to be a force. Newton says the force is gravity, let's see what happens. This result is from Kepler's data originally. Newton just said, my theory explains it. It's nice. Now, some other things that are interesting. We had said that we could talk about the gravitational potential energy as being this, minus g mm over r. And this is again taking the gravitational potential energy at infinity to be 0 as our reference point. And so basically this is saying that as we come, as we fall towards an object, our gravitational potential energy decreases. It's at its maximum, which happens to be 0, when we're not interacting, when we're way the heck away. So this happens to tell us one very interesting thing as related to escape velocity. Escape velocity is the velocity required to escape, shockingly enough, the gravitational pull of a planet or a star or what have you. So, if we think about this, if I'm on the surface of a planet, in a rocket ship, and I want to be in the stars, way up here, I need to get out of this gravitational well. Well, let's say that this is effectively infinity, and this is effectively, u of the radius of the Earth. So I need my change in potential energy to be whatever u of the radius of the Earth is, which means that if I'm going to get to infinity, not necessarily beyond, just to infinity, I need to have kinetic energy equal to my initial potential energy, how deep I am in the well. Technically, there's probably a minus sign there. Let's get rid of that with just thinking about magnitudes. So that would say that 1/2 mv escape squared is going to look like gmm over the radius of the Earth, or what have you. That's unfortunate. Let's say that's Earth. So escape velocity looks like this, which I'm now going to very quickly flip to a page in the book and make sure I'm not lying to you. Fantastic, it is indeed that. And this is true for any body you need to escape, whether it be a star, a planet, a moon, an ex-lover, who knows. Gravitationally, you probably have other, anyway, neither here nor there. This has a very useful thing because it tells you basically how fast your rocket has to go, or how much kinetic energy it has to start with in order to escape. If it has less than that, it's falling back to Earth. Even if it has more than that, it might fall back to Earth if you don't do it right. But also we should point out, usually you're not trying to get to infinity. You're trying to get to you're trying to get to an orbit a lot of the time. And so we want to kind of think about what kind of energy you need to get to orbit. And that gets tricky because now you have to get to a position with a velocity in a direction. So there's a whole lot kind of a fine order things going on here. But if we think about energy in an orbit, we know that we have this relation from before we were saying, where this has to hold true for our velocity and our position, which means that our kinetic energy, this 1/2 mv squared, has to look like, well, if I look at this, so mv squared looks like gmm over r. So my kinetic energy then has to be 1/2 mv squared, so 1/2 gmm over r. Well, at r, my potential energy is minus gmm over r. So my total mechanical energy at this position is minus gmm over 2r, half of that. This is your mechanical energy in an orbit. This takes into consideration not only how much gravitational potential energy you have in space, but how much kinetic energy you need to have in order to stay there. And again, if we need to go to semi-major for an ellipse, we can just switch r equal a. That's not how you spell circle. For a circle to ellipse switching. So that's kind of the spiel that they're going with here. It's a very neat thing when you think about it, that there is one specific energy for a given position. And if you have that energy and you're going in the right direction, you'll be in orbit. Of course, if you're going in the wrong direction, you might just be hurtling down towards the center of the Earth, which is really awkward. I should point out this won't get you into space, though. You need twice that energy to get to infinity, basically. Well, no, because it's a different r. I lied. Ignore that entirely. Different r's. So tricky things when we're dealing with gravity in general. And I guess I should point out at this point, what Newtonian gravitation actually looks like, and we have this functional form. Yay, gravity. Anyway, tricky things in dealing with gravity. There are a lot of r's that come up. There are a lot of radii. Sometimes they're in different things. When you have multiple objects, you have a law of superposition in play. So if I have, a moon, if I have another planet over here, it can be gravitationally attracted to the sun and gravitationally attracted to the Earth. And so the net force on it is the sum of those. Its gravitational potential energy is the sum of the gravitational potential energies. They add up as scalars, assuming that you've set them to the same reference point, which hopefully you have. So all of that stuff winds up being just additive. So that's kind of a happy way to think of it. Granted, with the forces, there's vector stuff to worry about. With the energy, Usually you don't add that stuff up as much. So yeah, most of these problems revolve around kind of clever applications of Kepler's laws and just some thinking of basic physics principles. We're thinking about orbits now, which means we're thinking about uniform circular motion and variations. We're talking about energy conservation. You know, it's the same big ideas, we're just applying them to kind of local scale space. So big, but not huge. Hopefully this gives you some kind of background and helps you out a bit. Good luck.